This is Chapter 3.1, Exponential Functions. The exponential function f with base a is defined by f of x equals a to the x, where a is greater than 0, a is not equal to 1, and x is any real number. For instance, f of x equals 3 to the x and g of x equals 0.5 to the x are both exponential functions. The value of f of x equals 3 to the x when x equals 2 is f of 2 equals 3 squared equals 9. We simply plug in 2 for x. The value of f of x equals 3 to the x when x equals negative 2 is f of negative 2 equals 3 to the negative 2 power equals 1/9. And just a quick reminder about negative exponents. Recall that they are 1 over the number to the exponent. So 3 to the negative 2 would be 1 over 3 squared, and that's 1/9. The value of g of x equals 0.5 to the x when x equals 4 is, and now is a good moment for you to locate on your calculator the button for exponents. Different calculators have different ways to do this. So take a moment to locate that on your calculator. You can press pause and work this out, 0.5 to the 4th power. Take a moment to do that now, and then resume when you have an answer. So you should have come up with this. G of 4 equals 0.5 to the 4th equals 0.0625. The value of x when 9 equals 3 to the x plus 1 is, now this is an equation, as you can see. We're trying to solve for x, but this might be unlike what you have seen before. What you have to do is you have to change the left side to have the same base as the right side, and then you'll be able to solve for x. So what we want to do is write 9 in terms of 3 raised to a certain power. And as you probably already guessed by now, that would be 3 squared equals 3 to the x plus 1. And then we can clearly proceed to 2 equals x plus 1, and therefore x equals 1. Another example, the value of x when 1/2 to the x equals 8 is, and once again we're going to change one side of the equation to match the other. So take a moment right now to write 8 in terms of 1/2 raised to a certain power. It's good practice. Press pause and then resume when you have done that. You should have come up with 1/2 to the x equals 1/2 to the negative 3. Because 1/2 to the negative 3 is 1 over 1/2 cubed, and that's the same as 8. And our equation is solved easily. X equals negative 3. Now let's look at the graph of the exponential function. And you'll want to remember this shape because whenever you see it, you'll know that you're dealing with an exponential function. This is what the graph looks like. It always intersects the y-axis at the point 0, 1. And the reason it does this is because if you raise a number, any number, to the 0 power, you get 1 as your answer. So whenever the x-coordinate is 0 for an exponential function, the y-coordinate will be 1, no matter what the value of a is in the exponential function. If you're interested in a proof of why any number raised to the 0 power is 1, you can ask in class, and I can show you then. Now the domain of the exponential function is written in interval notation. negative infinity to infinity, where negative infinity is the lower limit and infinity is the upper limit. The parentheses indicate the endpoints of the interval, but also show that those endpoints are not included, because of course you never actually reach negative infinity or infinity. The range of the exponential function is from 0 to infinity, to positive infinity. And the lower endpoint doesn't include 0, because the value of the function approaches 0 but never actually reaches it. Let's sketch the graph now of f of x equals 2 to the x. We can start, at least for now, we can start just with plotting some points. So let's choose some representative values of x. Negative 2, negative 1, 0, 1, 2. You see those on the left column. In the middle column, we see f of x. That's what happens when we plug in the x-coordinate into this exponential function 2 to the x. And we get 1/4, 1/2, 1, 2, 4. And then our third column is the ordered pairs. We can plot those ordered pairs, and that'll look something like this. And then finally, once we've plotted those ordered pairs, we can connect the dots, so to speak, with a smooth curve. And we have a graph of this exponential function 2 to the x. And as you can see, as is true with all exponential functions, the graph crosses the y-axis at the point 0, 1. Let's look at the graph now of 2 to the x minus 1 and see what effect that minus 1 has on the graph. Here's the graph of f of x equals 2 to the x. And here's the graph of g of x equals 2 to the x minus 1. And we can see that it's like the original f of x, but has simply been shifted downward 1 unit. So the graph of this function is a vertical shift down 1 unit of the graph of f of x equals 2 to the x. Now let's look at g of x, the function 2 to the x minus 1. And this time, the minus 1 is right next to the x. It's part of the exponent. Let's see what type of effect that has on our graph. So we graph f of x equals 2 to the x, as we did in the last slide. And then when we graph g of x equals 2 to the x minus 1, we see something that looks very similar, but it's been shifted over 1 unit to the right. So the graph of this function is a horizontal shift, right 1 unit, of the graph of f of x equals 2 to the x. Now, as you take notes on this, just keep in mind that at the end of these examples, I'll give you a little chart that will help you to keep straight these shifts and reflections. For now, just take notes on the slides. Let's look at the graph of g of x equals 2 to the negative x. First, as usual, we're going to graph our f of x equals 2 to the x, the normal exponential function. We'll see what kind of effect this negative x has. Well, it looks like 2 to the negative x is very similar to 2 to the x, except that it has been rotated 180 degrees around the y-axis. And that is called a y-axis reflection, or a reflection in the y-axis. The graph of this function is a reflection, or rotated image, of the graph of f of x equals 2 to the x in the y-axis. Now let's look at the graph of g of x equals negative 2 to the x. As usual, we graph our f of x equals 2 to the x so we can compare it to the function g of x. And when we draw the function g of x, this is what we get. Something that looks very similar to f of x, but this time it's been rotated 180 degrees around the x-axis. And this is called an x-axis reflection, or a reflection in the x-axis. The graph of this function is a reflection or rotated image of the graph of f of x equals 2 to the x in the x-axis. Now, putting it all together, we have this table. You definitely want to copy this down and use it as a reference for the classroom problems. A vertical shift is given by a to the x plus or minus a constant, where plus is an upward shift and minus is a downward shift. A horizontal shift is given by a to the x plus or minus a constant, where plus is a left shift and minus is a right shift. And notice the difference between vertical shifts and horizontal shifts. With vertical shifts, the plus or minus c is after the a to the x, whereas with horizontal shifts, the plus or minus c is actually part of the exponent. Moving on now with this table, a y-axis reflection is given by a to the negative x, and that's an image rotated on the y-axis. And an x-axis reflection is given by negative a to the x, and that's an image rotated on the x-axis. These are the classwork problems. Please copy them down now. You can start to work on them before class if you like, but there will be time to work on them during class.